Hemant, are you able to hear me?
Yes, ma'am. Good evening, ma'am.
Yeah, good evening. So we can continue on the discussion on the transformer as a two-port network and the remaining questions also from the practice. Okay. So did you try that electrical equivalent of a transformer? T network.
Up to up to lecture 6 complete, ma'am. Up to lecture 6. Mutual inductance in a transformer.
Okay. Lecture 7 is your electrical equivalent of a transformer, right?
No, no, I haven't seen it now, ma'am.
Okay. So we can today just once again part of that transformer we had already discussed. Again, once again mentioning the things that need to be discussed there, and then we can take the questions on the transformer from the practice assignment. Okay. So let me share my screen.
Ma'am, on a transformer discussion,
Uh,
please discuss what happens in the secondary winding of transformer. That is, it is in the lecture. It is given that opposing current is there. Something that is not understood, ma'am.
okay.
That portion.
So in the last class also we had discussed what has been conveyed through the lectures that if you want to have a good inductance, how do you do is you bind it over a ferromagnetic material, and it has been already discussed that for closed good path for the magnetic flux that will be achieved only for the configuration of if it is a that ring type or that what concentric that rectangular type. Okay, other than that, if you do it in this way, you will have leakage of flux. So we may not be going into those details because you have some other things also need to be discussed along with that leakage of flux. But anyway, in general, to make you understand, you will be taking a ferromagnetic material and winding the coil over it, and the two structures where that will be perfect coupling is the thing, that ring type or the other one rectangular, because there we get a closed path for the flux just like the for the current. Okay. And okay, so what we have in the transformer is you have primary side winding and secondary side winding, and they will be wound over the magnetic core. So those two windings, the primary winding and the secondary winding, will be tightly coupled, and we have n1 number of turns referred to the primary and then 2 in the secondary. Then we discussed that the voltage per turn will be the same. So that means V1, if it is the voltage on the primary side, N1 is the number of turns in the primary. So V1 by N1 is the voltage per turn. Similarly, on the secondary side, it will be voltage per turn is V2 by N2. So V1 by N1 is equal to V2 by N2. That we alternately write it as V1 by V2 equal to, sorry, small, N1 by N2. Then, with reference to the while discussing the magnetomotive force, the MMF is if you have n number of turns and the current I is flowing through that coil of having n number of turns, the MMF will be N into I ampere turns. Ampere turns will be the unit of MMF. So Ni, so N1 I1 will be the ampere turn associated with the primary. I mean magneto MMF associated with primary, and N2 I2. So N1 I1 will be equal to N2 I2, from which we will get N1 by N2 equal to I2 by I1. So that we here, if you put it here in this equation, you will have V1 by V2 equal to N1 by N2 equal to I2 by I1. This is the fundamental thing we have seen. Then we came across the mutual inductance. Because of the tight coupling between the primary and the secondary winding, what we will have is, if we consider the single inductor of L1 Henry and a current I1 is flowing through this, and we have the voltage across it is V1, we write it as V1 equal to L1 dI1 by dt. Similarly, we have another coil L2. So here we write it as L2 dI2 by dt. Now in the case of transformer, we have primary as well as secondary winding, which are tightly coupled to each other. So N1 is to N2. So here we write V1 equal to L1 dI1 by dt, plus we will have some effect of this current I2, for which we are written it will be some term into dI2 by dt coming for the coming in the equation of V1. Similarly, V2 equal to L2 dI2 by dt plus some impact of this I1, the current in the primary. And in this place, we had later filled the term M, which is referred as the mutual inductance. So L1 and L2 are referred as the self inductance of the coils. Self inductance of the primary and secondary windings. M is referred as the mutual inductance. So what we say is, if they are perfectly coupled, I mean tightly coupled, we say that coefficient of coupling K to be equal to 1. Otherwise, we have a fractional value for that. So K is the so this mutual inductance, it depends on the coefficient of coupling, and is given as, tell me.
It's root k into root over L1 L2, ma'am.
K into root over L1 L2. So M is the mutual inductance, K is the coefficient of coupling, L1 and L2 are the inductance of the two windings. What else we have seen? Yeah, then uh, yes, in the S domain we have written the equation here. If we have this V1 equal to L1 dI1 by dt, so we know that V1 of S we can write it as S L1 I1 of S, correct? This one V1 is L1 dI1 by dt. So in the S domain I can write it as V1 of S SL I1. So V1 of j omega will be the phasor domain j omega L1 I1 of j omega. So accordingly we will have for the transformer V1 here, if we write it as, what we have is j omega L1 plus j omega m I2 of j omega. V2 is j omega L2 So as such directly we get the set parameters. So V1, V2 equal to j omega L1, j omega m, j omega m, j omega L2, I1, I2. So this is set 11, set 12, set 21 and set 22. Then we next is the homework that we were discussing, which I asked you to do the last. That means even in the lecture, profs have asked you to do. That is the T network, alternately representing the electrical network equivalent of the transformer in the form of a T network.
Ma'am,
Ah,
ma'am, in the place of S, we have written j omega, na? That means complex form, na, ma'am, it is.
yes, phasor. In
Phase,
first we have written this one. Understanding for a single inductor, then we applied it for the transformer. So here while we applied it for the transformer, we wrote it as I2 will also have some impact on this V1. Similarly, I1 will have impact on V2, and that is with reference to this term mutual inductance M. So M will be mutual inductance and L1, L2 the self inductance. Then we wrote it in, if these are the expressions for V1 and V2, we wrote them in S domain. We know that di1 by dt it is SL, right? So V1 of S, SL1, I1 of S, all those things we have written. Then for S, we have substituted j omega. That means in the phasor notation, we have written this. So accordingly, we get this. So in effect, this gives you directly the impedance parameters, because you know there we write the expression for V1 and V2 in terms of I1 and I2. So accordingly, we will get this as set 11, set 12, set 21, and set 22. So this is V2, I2. So this was a thing we had discussed in the last class to do it as a homework, right? We represent this transformer electrically, so that we can analyze this by applying nodal and all, so that this is the electrical equivalent of the transformer in form of a T network. So the component values of that T network, I have chosen it to be LA here, LB here, LC here. Okay, so now you have to find out the values of LA, LB and LC. How to do that? The fundamental idea also we mentioned in the last class. That means already you know the set parameters of the transformer. So the same transformer is now by this T network is alternately electrically represented this way, so that this T network will have the set parameters same as these values. So you have to equate the set parameters of this T network to these values, and accordingly you can find out LA, LB and LC. So I will, those who have not tried out with this idea, just right now try it for some 5 minutes, after which I will discuss what are the values for LA, LB and LC. The fundamental idea is, you know, just now we had come to the point where the set parameters of the transformer our Z11 is j omega L1, Z12 is j omega M, that is equal to Z21, then Z22 is j omega L2. So this T network, which is an alternate way of representing the transformer, will also have the same set parameters. So equating the find out the set parameters of this T network, equate it to these values so that you will get the values of LA, LB and LC. How to find out this T network? We had already seen through one of the assignments also. ZA, ZB, ZC, the T network, right? The 26th or 27th question from the practice we had done. Asking for which of the statements is true or false. Z12 equal to Z21. We had done it. So you can just refer to that for doing the set parameter of this T network. Find it out, equate it to these values, and then you tell me what are the values for LA, LB, and LC. Is it done?
No.
Ma'am, L1 is equal to LA plus LC.
Correct.
M is equal to LC. L2 is equal to LB plus LC.
Correct. From which we want LA, LB, LC in terms of L1, L2, and M. That is the thing being discussed in the lecture, right? You want these values in terms of as functions of L1, L2, and the mutual inductance M. You have to find out
So
the values
L-
of LA, LB, and LC in terms of the self-inductance L1, L2, and the mutual inductance M.
So L A is equal to L1 minus M.
Okay.
L2 is equal to
LB.
no sorry LB is equal to L2 minus M.
One second, is this the way you have also taken? Is my LB same as your LB? Right? This is
Yes,
LB?
ma'am. Yeah.
Yeah, so LB
Yeah.
is
L2 minus M.
correct. And LC will be
M.
correct. Keman, did you get the idea?
No, I am trying like as shown in the lecture, ma'am, by sorting V2
Yeah, fine.
second port and calculating the
Yeah,
equation.
take your time and then find it out. Then we can
Okay.
proceed.
We can just apply, ma'am, KVL in both the loops.
Correct. KVL and both the loops you get expressions for V1 and V2. Then you
Yeah.
match the set parameters with these values, already known values.
Yeah.
But remember, this will be the case when the M is positive, the flux is additive. This L1 minus M for LA and L2 minus M for LB and M for LC is the case for M positive.
Positive.
Okay.
So if M is negative, then it just becomes minus JWM
Yes. So
Z12.
what do you get? Obviously, the values
So
will
it will
change
be
it
plus
as
L1 plus M.
yeah, L1 plus M, L2 plus M, and minus M.
Yeah.
Did you get one of
Ma'am,
these?
ma'am, in the equation, ma'am, V1 equal to I1 LA
Yes.
plus LC into I1 plus I2 will come, na, ma'am? Or I2 will 0, ma'am? Here. Because V2
I2
is
will come.
sorted. V2 is sorted.
So if I write the KVL equation, will be the KVL equations. V1 will be
I1 LA
I1
LA
LA.
J
plus
omega.
LC.
J omega. We have to take it in the. Let me first represent this directly as S domain T network. So SLA, SLB, and SLC. So here S I1 into SLA. And now tell me the equation. KVL. I1 into V1 is
SLA
yeah.
plus SLC I1 plus I2.
So that will be I1 into SLA
SLA
plus SLC plus SL
SLC I2.
SLC I2. Correct. Then V2
SLB I2
SLB I2
plus SLC I1 plus I2.
So that will be SLB plus SLC into I2
plus SLC I1.
SLC I1. So here this coefficient will be your Z11, right?
Yes.
Z12, Z21 and Z22. So what did you have here? Z11 is J omega L1, that is SL1. So SL1 equal to SLA plus LC. Similarly, what do you have? J omega M. So SM equal to SLC. And you have SL2 equal to S into LB plus LC. Then, so directly from 2 we get LC equal to M. Then 1 will be LA plus LC equal to L1 and LB plus LC equal to L2. So LA will be L1 minus M, LB will be L2 minus M. So your electrical equivalent will be
Please, so the
LA equal to L1 minus M, LB equal to L2 minus M, LC equal to M. So you have to do it separately for further understanding. That means Z11 is obtained by Z11 is V1 by I1 um, with the constraint I2 is 0. That means this port is being open circuited. So you make I2 0 open circuited, then you find V1 by I1 to find Z11. Similarly, when the port this port is 0, that means I2 is 0, this port is open circuited, you will have Z21, right? Correct. Similarly, you find out make this port open circuited, I1 make I1 0 and find out the other two set parameters. That is the way it's discussed in the lecture, correct? I2 making I2 0 so that there will not be any current flowing through this inductor IB, so that this plus this will give you L1. That is what we have written. L1 is SLA plus LC, LA plus LC. So this is the case for M is positive. If M is negative, L1 will become, sorry, LA will become L1 plus M, LB will become L2 plus M, and LC will become minus M. And finally, we have to discuss about the impedance matching in the transformer.
If M is negative, ma'am, what?
Everything will be here. You will replace M with minus M. So LA expression will become L1 plus M, LB will become L2 plus M, and LC will become minus M. That means the case that dot you had. This is the case. First, that L1 minus M, L2 minus M is this is the case that explaining by means of the dot convention. If you have the dots here, that means one current is entering and other is coming from this side, entering from this terminal, but not from this. So that will be fluxes opposing. So that you will have these expressions for LA, LB, and LC. That is L1 plus M, L2 plus M, and LC is minus M. Impedance matching in a transformer. If you have gone through, please explain what you have. If you say have some resistor connected in the secondary side, how do you interpret the value from the primary side? That is the basic thing. So the fundamental idea behind this, you have you will be equating the power loss on both the sides, right? The power equations. So V1 I1 equal to V2 I2. So what you have say in the lecture for easy understanding, what has been discussed first is you connect a simple 1 ohm resistor in the secondary side. So you will have it like a load there. So if we connect a 1 ohm resistor in the secondary, here we have the primary voltage V1, the current flowing through the primary is I1, and in the first case we are considering the simple case where N1 is to N2 is 1 is to 1, so that I2 right now I'm not considering in this direction, since this 1 ohm acts as a load resistor. We are showing like this, I2 is flowing through this 1 ohm, so I2 direction is towards right hand side. So N1 is to N2 is 1 is to 1, so that I2 will be equal to I1. Here is our V2. So V1 by V2 equal to N1 by N2 equal to I2 by I1. So this will be just same as you have a V1 here and 1 ohm connected. Okay, this will be the resistance seen from the primary side, 1 ohm. Now if you consider N1 is to N2, not 1 is to 1. So the primary current is I1, primary voltage is V1. Then here you connect a resistance R. You have to see what is the equivalent resistance seen from the primary side. The current in the primary is I2, and this is your V2. So just as we already know, the volt per turn will be the same. So V1 by N1 equal to V2 by N2. Then you have V1 I1 equal to V2 I2. So accordingly, what will you have for R equivalent?
I have a above equation not understand. Previous equation.
Which one? This one.
Previously.
V1 by N1.
No. Scroll up. Previous diagrams. That equation not understand. Equation is okay, but the concept.
No. Here we are right now discussing the impedance matching in a transformer. That means we are trying to we have connected a resistor of say R in general. The second case in the secondary, then what will be the equivalent resistance seen from the primary, we need to understand. That is the case of this impedance matching. Okay, so to try to understand that, we are considering the simple case. We have connected a 1 ohm resistor in the secondary, and we have considered the case where the turns ratio n1 is to n2 is 1 is to 1, so that the primary voltage is marked as V1, the primary current as I1, with the turns ratio 1 is to 1. The secondary current I2 flowing through this load resistor 1 ohm will be same as I1, because we know that ampere turn relation. So that V1 by V2 is equal to N1 by N2. So 1 is to 1 being the ratio, that will be equal to I2 by I1. So I2 will be same as I1. All these things is clear, because we already know these relations, right? The voltage per turn is the same, and then by equating the MMF, we know that V1 by V2 equal to N1 by N2 equal to I2 by I1. So in effect, V1 by V2 will be equal to I2 by I1. Here what we had discussed. Then the second case, we try to understand if a resistor R is connected at the secondary. In place of 1 ohm, right now it's a resistor R in general. Then what will be the equivalent resistance seen from the primary? So accordingly, what you will have, and here also it is not the turns ratio is not 1 is to 1, but turns ratio is N1 is to N2. The primary number of turns is N1, and the secondary number of turns is N2. So the turns ratio is now N1 is to N2, not 1 is to 1. One second.
R equivalent is equal to R by R into N2 by N1 whole square.
What we were discussing, number turns ratio is N1 is to N2, and I have connected a resistor R. So here again, the same voltage per turn is the same. So V1 by N1 equal to V2 by N2, and your MMF, that is your I1 N1, is the MMF referred to the primary, and I2 N2 is that referred to the secondary. So MMF being the same, I1 N1 equal to I2 N2, so that we have the power loss in the secondary will be I2 square R or V2 I2. If in terms of VI product, V2 I2. So what we have is I2 square R equal to I1 square R equivalent. So what you will have, R equivalent will be R into N1 by N2 the whole square. Correct? V1 I1 and V2 I2 is, we have equated the power. That means whatever power is dissipated in this resistor connected in the secondary, that power has to come from the primary side. So V1 that power on both sides, primary side and the secondary side, can be equated. So V1 I1 is the power referred to the primary, and this is referred to the secondary. So that in terms of this current and resistance here, so I2 square R will be on the secondary side, that is equal to I1 square into R equivalent. So R equivalent will be I2 by I1 the whole square. So I2 by I1 is nothing but N1 by N2. So N1 by N2 the whole square. So if you see, if you substitute here for R 1 ohm, what do you get? R equivalent will be 1 ohm into N1 by N2 the whole square, and N1 by N2 was 1 is to 1, the first case where we had seen. So you will get simply R equivalent as R. That means that 1 ohm is just seen as 1 ohm on the primary side. If you connect any other resistor by means of this impedance matching relation, R equivalent is R into N1 square by N2 square. That will be the resistance seen from the primary side when you connect a resistance R in the secondary. And this is the basic behind the impedance matching between what any succeeding functional blocks. I mean, if you connect two functional blocks, the output impedance of the first should match with the input impedance of the second block, right? So those things and all this will be the thing behind, fact behind. Okay.
So here, ma'am, what we have calculated input impedance, ma'am.
Here, if we connect a resistance in the secondary, what is the resistance seen from the primary side?
Resistance
This
means can we
this
consider
this
this as
R this
load?
R this R connected in the secondary. What will be the value of that R seen in the primary side? So that will be given by this equation. So what will be the turns ratio given? Accordingly, you will have this R equivalent. That will be the resistance value for this R in the primary side. Okay.
Yes, ma'am.
So I think some last 5 or 6 questions from practice we need to do based on this transformer. Shall we take one by one?
Yes.
So 29, I think. Yeah, 28. Yes, 29. Let me give this a For the following two-port network, the value of equivalent inductance between terminals 1 to it is 1 and 2, 3 and 4 okay. The value of equivalent inductance between terminals 1 and 2 is 4 Henry with terminals 3 and 4 open circuited, and it is 3 Henry with terminals 3 and 4 short circuited. The coefficient of coupling is if Ls equal to 2 Henry. So the T equivalent circuit will be this is LP minus M, this is LS minus M, and this is M. So the equivalent inductance between terminals 1 and 2 is 4 Henry with 3 and 4 open circuited. So that means L12 is 4 Henry. So when this is open circuited, when 3 and 4 open circuited, or I2 is 0, L12 is 4 Henry. So that is equal to LP minus M plus M, because we already discussed while deriving that with these terminals or this port being open circuited, I2 0, there will not be any current flowing through this. That means this plus this will give you the equivalent inductance in the primary. That means between 1 and 2, that is given to be 4 Henry. So that means LP is 4. Similarly, with 3 and 4 short circuited, it is 3 Henry. So that will be LP minus M plus M parallel LS minus M. Just see how this came. You just derive this and see when the terminals 3 and 4 are short circuited, the equivalent resistance between the terminals 1 and 2 will be LP minus M plus M parallel LS minus M. Correct? This short circuited means this LS minus M comes in parallel to M, then that will be in series with LP minus M, and that is given to be 3 Henry. So that is being equated. So LP minus M plus M parallel S minus M. So that will be M into LS minus M by M plus LS minus M. So M and minus M gets cancelled. So that will be in the denominator LS. So LP minus M, then plus M into LS by S, that will be plus M, then minus M square by LS. Then for LS, it is 2 Henry given. So minus M and plus M gets cancelled, and this will be M square by 2. We got LP as 4. So LP is 4. So 3 equal to 4 minus M square by 2, from which we will get that mutual inductance as root 2. Then coefficient of coupling will be M by square root of L1, L2. Next question. The primary winding of a transformer with turns ratio 1 is to 10 has a 120 volt AC supply. The value of the secondary voltage is.
Please scroll up, ma'am, for L12 is equal to 4 Henry. Please scroll up for open circuit, ma'am. Please. Here what happens, ma'am? L12 is equal to 4 only when it is open circuit.
It is given.
Here LP minus M plus M is written, ma'am.
LP minus M.
Plus M written. LP minus M plus M.
That is what, when this 3 and 4 terminals are open circuited, this secondary current I2 will be 0. That means there will not be any current flowing through this LS minus M. Then this and this added will give you the L1. Remember what has been discussed in the lecture for deriving this L1 minus M, L2 minus M, correct?
Yes.
Adding these two will give you the L1, correct? Primary winding.
Yes, ma'am.
When it is open circuited, this port. Similarly, being symmetrical the other way out, you will have these two sum for this secondary. So 4 into 2, 8. That is what here I have substituted. Is it clear?
So L1 means LP and L2 means LS.
Yes. Because we how do we get? By adding this. When this is open circuited, LP minus M plus M will give you L1. Similarly, the other way out, adding these two will give you the secondary. And the secondary is given to be 2 Henry, LS.
Second, ma'am. Initially 3 and 4 are open. Okay. So from primary side, it is
LP minus M plus M, that is LP is L1.
yes, ma'am. And next, ma'am.
So LP we have got it here 4 Henry.
Yes.
Similarly, LS minus M plus M will give you LS, which is L2. LS is 2 Henry given. So L2 is 2. So root of L1 L2 becomes root 8.
Yes, ma'am.
N1 is to N2 is given as 1 is to 10, and the primary voltage is given to be 120 volt. Secondary voltage is being asked. So you have V1 by V2 is N1 by N2. So V2 will be V1 into N2 by N1. So that will be 120 into 10, 1200 volt. Two 2 Henry inductance coils are connected in series and are magnetically coupled to each other. The coefficient of coupling is 0.1. The total inductance of the combination is so L1 equal to L2 equal to 2 Henry. Coefficient of coupling is given to be 0.1. So mutual inductance will be K into square root of L1 L2, that is 0.1 into square root of 2 into 2. So 0.2 Henry will be the mutual inductance value. When these 2 Henry coils are connected in series, it will be L1 plus L2 plus 2M. That will be 2 plus 2 plus 0.4. So 4.4 Henry. The value of L equivalent for the circuit shown. I will draw the circuit first. So this is the given circuit. The dot convention is also shown. You have to find the L equivalent. So in order to apply some KVL also, you can maybe connect some 1 volt source or something at the input as a test source, and then you can apply KVL. V1 equal to J5 I1 plus J5 I1 plus J5 I2. J5 into I1 plus I2. So that will be J10 I1 plus J5 I2. Then mesh 2, you have 0 equal to J3 I2 plus J2 I2 plus
So J5
J5 I1. Am I right? J5
because it's negatively matched, coupled.
Soumendra, are you telling something?
Yes, ma'am. It's in the question. It is negatively coupled. So J5 I2 should be negative.
It's not the I mean dot convention is the reverse, right?
Yes.
Like this.
Okay. So yeah, it will be okay. Okay. So then that is why it is plus.
Correct.
Otherwise, it would have been minus.
Yes.
Okay.
0 equal to J5 I1 plus J5 so I1 equal to minus I2. If you substitute it in V1, V1 will be J10 I1 minus J5 I1. So that will be equal to J5 I1. So input impedance will be V1 by I1.
But when it is positively coupled, then V1 is equal to L1 di by dt plus M di2 by dt, right?
When it is
When it is positively coupled,
correct,
then it is L1 di by dt plus M di2 by dt.
correct,
Then when it is positive, then it is plus M, right? V1 is equal to Li di1 dt plus M di2 by dt. So when it is negatively coupled, V1 should be Li di1 by dt minus M di2 by dt. So then it becomes minus the mutual inductance when it is negatively coupled. So
But
then
here
it is,
you have, I mean, see, I will show you these two cases. This, if you see like this, I1, what is being entering, and this I2, this will be M positive.
yes.
That M negative can be shown like this in two ways. One is like this, I1, and the other is I2 from this side. Okay.
Okay.
Or it will be like this. Correct?
Okay. Okay. So
Then
when
it's
I2 is leaving, then M is negative.
so is it
No.
fine right now?
Ma'am, can you just scroll up? So is I2 leaving or entering? No, in the question, ma'am, that you have taken. So over here, I2 is leaving, right?
Correct.
So if I2 is leaving, then it is negatively coupled. So the equation that will
I2
be
is leaving, but
Hmm.
it's shown with the opposite dot convention also, right?
So that means that it is minus I2 in your diagram.
Yes. So in effect,
So
it
that,
becomes plus, right? This I2 is leaving, and it's also shown like this.
but why did you take I2 leaving, ma'am? Why did you not take it as entering?
Because of this load here.
Ma'am, here dot may be regarded as a entering current, na? That is positive side, na, ma'am?
The dot, one is here and the other is here, means it should be like this. Leaving. I mean, flowing into the 3 Henry.
But ma'am, why are you assuming that I2 is flowing into 3 Henry? We don't know the voltage if it is positive on the upside or it's on the downside.
I think that is because of this dot convention basically given, and otherwise also uh,
Yeah, so we just have to follow the
this
dot
load has to
convention.
draw current, right? 3 Henry. Correct?
No, that is not. That depends on what your voltage inducting. That voltage is inductance voltage. It can be positive on the.
Fine. Then you don't take it in that way. You just go with the
Hmm.
dot convention.
Yeah, so if I take the dot convention only, then I have to take V1 is equal to L1 di by dt minus M di2 by dt. If the dot was if it was positively coupled, if the dot was above, then I would have taken L1 di1 by dt plus.
But here it is given na positive. Correct?
So if M is given as positive, then we ignore the dot convention.
Not like that. I mean, with this M value positive and with the dot convention like this, the equation would obviously result like this here plus.
Okay. So because the dot is given like that, that is why I2 is taken as
Right words.
no, sir. Then if dot is down on the secondary transformer, so then that means positive is below and negative is above.
Positive is below and negative, and why?
That is the dot. So if
One second, one
like
second.
on the
Uh,
primary side, if the dot is above,
just
that means the positive is above and negative is below for the primary. Similarly, if dot is below, that means the positive is below.
one second. Here for 3 Henry, the plus is at top, right?
Yeah, no, for the Yeah, no. So for the 2 Henry, positive is below and negative is above. So then that your current convention is right, because negative is below and positive is above.
Correct.
So then it's going to flow into 3 Henry from above the
Correct.
current.
So that it will result
Okay.
in this equation only, right?
Yeah, so that means that in the question, if M is given as positive, we'll just take it as positive then. We won't
Correct.
worry about the
Dot.
dot convention.
Yeah.
Dot convention we'll only worry about for the current direction.
Yes.
Okay.
Ma'am, please scroll up, ma'am, for mesh 2 equation. Please scroll down. Ma'am, here, ma'am, input impedance equal to V1 by I1 equal to
J5. Here
J5.
V1 equal to J5 I1 we got it got right, because we got it as I1 equal to minus I2. So substituting here for V1, we will get V1 is J10 I1 minus J5 I1. So that is J5 I1. So V1 by I1 is J5. So J omega L equivalent. So L equivalent will be 5 Henry.
Ma'am, how, ma'am, J5 equal J omega equivalent, ma'am?
Which one? Here
J5
the
equal.
input impedance we have taken in general. We here you see this circuit. This is the L equivalent. V1 by I1 will be that impedance is here L equivalent. L equivalent in terms of I mean XL is J omega L, right? Correct.
Yes, ma'am, SL or J omega L.
So that is J omega L equivalent. So from which we will get L equivalent is 5 Henry.
Okay, ma'am.
Then 33. An ideal transformer of n is to 1 turns ratio is to be used for matching a 4 plus J3 ohm load to a voltage source having 3 plus J4 ohm internal impedance. For what value of n is this matching possible? Second, what was the load impedance? An ideal transformer of n is to 1 turns ratio, okay, is to be used for matching a load impedance is 4 plus J3 and the source impedance is 3 plus J4. And n is to 1 is the turns ratio. Fine. N is to 1 is the turns ratio. Load impedance is 4 plus J3 ohms. Source impedance is 3 plus J4 ohms. So this means magnitude of the load impedance will be 5 ohm, and magnitude of the source impedance will also be 5 ohm. So what we have is for matching ZL by 1 by n square equal to ZS. So
Ma'am,
what
please
did we get
explain.
here? R equivalent. R equivalent is R equivalent by R, where R equivalent is the primary side and R is the secondary side. Okay, equal to n1 square by n2 square. So here, what do we have? R equivalent is primary means here source. Okay. Yeah. So what we have is R equivalent is R into n1 by n2 the whole square. This is the secondary, this is the primary. So here source ZS equal to ZL into n1 by n2 the whole square. Here turns ratio is what? N is to 1. That means n1 by n2 is n is to 1. n1 is to n2 is n is to 1. n1 is to n2 is n is to 1. So ZS equal to ZL into n the whole square. That is ZS ZL equal to n square. That is what I have written here. So that is equal to 1. So n will be 1. Is it clear? Impedance matching.
Here n equal to root over ZS by ZL. N equal to root over ZS by ZL.
That is equal to 1. Here given, right?
Yes, yes, ma'am.
Ma'am, some clarity of question 32 I wanted to ask.
You are not audible.
Ma'am, on question 32, I had some doubts, ma'am.
32. What was
previous
32?
question. The previous
This
question,
one,
ma'am.
this dot convention, right? Just now we
Ma'am,
had discussed.
if this was positively coupled, what would be the difference in the equations?
If it is negatively coupled,
Though in the question it is giving negatively coupled, if it was positively coupled, what would have been the difference in the equations?
I mean, you say M is negative.
No, M is positive, and if both the dots were above, if it was positively coupled. Now it has been given as negatively coupled.
Then wherever you had I1 plus I2, you will have I1 minus I2, right?
No, so V1 does not depend on the direction of I2. It only depends on the mutual inductance, right? It only depends on the value of M,
Yes,
correct?
correct.
So if M is positive, so V1 equation would have still remained the same. or would it have changed?
Yeah, come again once again.
If both the dots were above, then would
Okay.
the V1 equation change with M as positive? The V1 equation that you have written below, ma'am,
It
would it
will.
still remain the same?
Then we would have taken anti-clockwise for I2, right? That will make change in equation. Am I right?
Hmm.
If both the dots were above,
Hmm. If both the dots were above, then I2 would have been entering the 2 Henry, right? Like it
correct.
has been given in the
That means
lecture,
the anti-clockwise direction for the mesh current I2.
I2 correct. So if I refer to this lecture of mutual inductance, then the V1 is L1 di1 by dt plus M di2 by dt for the positively coupled transformer, correct? Where I1 is entering and I2 was also entering the inductance.
Okay.
So then the V1 over here is positive for the mutual inductance also, right? Plus M I2.
Yes.
That
Yes.
is right.
Hmm.
So then the equation remains the same for V1,
Let
even
me
if the
just check
dot
it
is
out.
above.
Yeah, give me 1 minute. Let me just check it out.
I am here. Here, both primary and secondary in winding, ma'am. If dots are at the same position, I think that it is M is negative, ma'am.
They are not in the same position, right? Here, this is
Now
the
it is not
terminal.
same position. That means M is positive, additive.
Yes,
Because if they are in the same direction, that is plus minus and plus minus on both primary and secondary, then
correct,
mutual inductance will be that will be decreased. Overall inductance will be decreased, no, ma'am.
correct.
If they are in opposite direction, that will be mutual induction will be added to the self inductance.
Yes. So with regard to this one, Soumendra, let me just check it out. I
Yes,
also right
ma'am.
now got stuck because thinking the other way. Just give me. I will either clarify thinking it today or the next class I will clarify. As you may have mentioned, I am also right now. Means you
Sure,
are
ma'am. Sure.
asking the other way out, right? Yeah, I understand.
Correct, ma'am. Because I'm referring to week 11, lecture 6, mutual inductance in a transformer. So I'm looking at those equations where
Yeah,
the
yeah, I understand.
positive
I
coupled
understand.
inductance.
Yeah, just
Okay, ma'am. Thank you.
uh, yeah. We'll just go through and clarify. You remind me when we have Monday, right? Yeah, I will keep it in mind. No problem. I will just let you know.
Thank you, ma'am.
What else? 34. One more question we have, right?
Yes, ma'am.
The magnitude of the input impedance seen by the AC source in the circuit. Let me just see the circuit. Magnitude of the input impedance seen by the AC source. Okay. Okay. So First, let me draw the circuit. So here in the secondary side, what we have is a resistor of 8 ohm and an inductance of 4 ohm. So if that is reflected on the primary side, secondary circuit reflected on the primary side will be you have already this 4 ohm, then this source, say this will be some R dash and X dash. Just like we have seen in the impedance matching, R equivalent, when R was connected in the secondary, taking it to the primary, it was R equivalent. Similarly, this 8 ohm, which is connected in the secondary, becomes R dash in the primary, and this 4 entry connected in the secondary becomes X dash in the primary. So now what will be this R dash? It will be this
R into N1 by N2 whole square.
R2 by N square. So that will be 8 by 2 square. So you will get it as 2 ohm. Similarly, what do you have for X dash? It will be now impedance seen by the source will be
Root of 2 square plus 1, root of 5.
equal to 4 plus this R dash plus X dash. So 4 plus 2 plus J1 ohm. So that will be 6 plus J1 ohm. So input impedance will be magnitude root of 37, some 6.08 or something you will get. So this is again based on that impedance matching. I think it's fine for you. Any clarification?
What I did was, ma'am, I took the magnitude of 8 plus J4 and then I then I multiplied it by N1 by N2 whole square, which is divided by 4. Right, so it was coming as something 8 plus J4 divided by 4 will be 2 plus J. So root of 4 plus 1, which is root of 5. 2.23 plus 4 is 6.23.
You directly took it as this. What did you say? 8 plus this one, right? 8 plus
8 plus
4,
J4
and then
divided by
you
4.
took it as okay. Yeah.
Right, so it is 2 plus J.
Yeah, again you will get
Okay.
some 6 point something, 6.23 you get, right?
2 plus
Correct?
j. Yeah, ma'am. Okay, yeah. I did the mistake that I first took the magnitude of 2 plus j and then I added to 4.
Yeah,
So
yeah.
first I should have added to 4 and then took the magnitude.
Correct.
Okay, got it.
Ma'am, in the equation R equivalent equal to R into N1 by N2 whole square, ma'am. This is also applicable if we consider equivalent resistance from secondary side, ma'am.
No, it will be the other way out. It will not be the same. Here we take it as what is being connected in the secondary, how it is reflected in the primary.
R equivalent here is primary. For secondary, ma'am, that will be different, no?
Yes, it will be different.
Okay, ma'am.
So,
Ma'am,
how are the? Tell me.
in the graded question, ma'am, there may be a mistake, or it may be that I'm doing it incorrectly. Question number 10.
Of week 11 or week 10, 12 you are
Week,
telling about?
week 11, ma'am.
Week 11 graded question 10.
Question 10, ma'am. I am getting something in the denominator. I'm getting R1 in the denominator.
It was also asking for some N1 and N2 values, if I remember the question, right?
Y21. The Y parameter Y21 it was asking for.
Y21, is that the last question? No, some
No.
asking.
Question number 12, 10.
One second. Let me just open it for you. Graded 11.
In the graded, ma'am.
Yeah.
Yes, ma'am, this one.
This one you are getting R1 in the denominator.
Yes, ma'am.
Yeah, I will check it out.
Okay, ma'am, thank you.
Okay, so this one thing I need to clarify on Monday, right? This dot convention.
Yes, ma'am.
Yeah, I will keep in mind. So we will be again meeting on Monday. So please submit the assignment tomorrow, and your mock paper will be mostly released within 2 or 3 days. So this time maybe we will try to make it a timed mock paper so that you can attend it like an exam. That we will let you know. Okay. So accordingly, you can start preparing also. And once week 12, the 2 sessions are also over, we can start the revision sessions. I think I am planning from Tuesday or next Thursday. The revision sessions. Fine.
Okay, ma'am.
Yeah. Thank you. Thank you, Hemant.
Thank you, ma'am. Thank you.
Yeah.
Thank you, ma'am.
Yeah. Good night.
Good night, ma'am.